Here's what I want to do. I want to evaluate this integral with this vector field from the point 0, 0 to 1, 1. So I'm going to do it on three different paths. I'm going to find that integral for the path from just y equals x. That goes from 0, 0 to 1, 1. X equals y squared and y equals x cubed. We'll do those each in turn. So first of all, the path y equals x. So of course, if we wanted to look at a picture of what that looks like, it's just a straight shot. Kind of the most simple path, okay? So it goes from 0, 0 to 1, 1. And what I'm going to do is I'm going to look at the integral in the differential form. So I'm going to look at the integral like this. I'm going to say, okay, this is 1/2 xy dx plus 1/4 x squared dy. Okay, so I'll just look at that integral in that form. Now, first of all, one of the things we note here is y equals x, so dy equals dx. We're going to need that here in a minute. So here's what I've got. I've got 1/2 xy, so I'm going to do 1/2 x, and in place of y, I'm going to put x because y equals x, and then I'll put dx there. And then I've got 1/4 x squared, and in place of dy, I'll put dx because we just found that to be the case. And obviously here, I'm integrating with respect to x, so I'm going to make this from 0 to 1, see, because I'm looking at the x from 0 to 1. I'm looking at the x coordinate. So when we do that, we get the integral from 0 to 1, and that's going to be 1/4 plus 1/2, so that's going to be 3/4 x squared dx, because we've got 1/4 x squared here and 1/2 x squared there. 1/2 plus 1/4 is 3/4. Okay, now let's see what this is going to be. If we integrate this, this is going to be 1/4 x cubed from 0 to 1, which is just 1/4. Of course. There we go. So that's the result. Now I want to look at this next path. And this next path, we're going a little bit, not a straight line, but a little curve here. So, but we still go from 0 to 0, from 0, 0 to 1, 1. So there's what that path looks like. And this time I noticed that dx equals 2y dy. So it looks like now I'm going to be integrating with respect to y, just because it was easy for me to find out what dx is. Okay, so let's see what we've got here. I've got the integral, and my path this time is going from 0 to 1 for the y's this time. Okay, so I'm going from 0 to 1, and I've got xy. Now, in place of x, I'm going to put y squared. So I've got 1/2 y squared y, and in place of dx, this dx right here, I'm going to put 2y dy. So here is 2y dy. And then I've got 1/4 x squared. So 1/4 x squared, that would be y to the 4th. Yeah. And then just the dy there. Okay. So if I didn't make any mistakes, there's what we have. So in place of x, I put y squared, and then y squared squared is y to the 4th. So let's see what we've got now. We've got the integral from 0 to 1, and I've got y 4th, okay, y 4th dx, dy. See, because the 2's cancel, and then I've got y cubed times y, that's y to the 4th. And then we've got a plus 1/4 y to the 4th dy. So if we put all that together, we've got the integral from 0 to 1 of 5/4 y to the 4th. And then that will give us, if we integrate, we are going to get 1/4 y to the 5th from 0 to 1. And once again, that's 1/4. Okay, so 2 times we've got 1/4. Now, let me look at this other one. Y equals x cubed. So we're going on a little bit different path. Still, we're looking at this part where we got this cube function. So let's see what we've got. Whoops. Okay. Now notice that dy equals 3x squared dx. So it looks like I'm going to be integrating with respect to x this time, because it's going to be easy for me to substitute the dy. So here I go. I've got 1/2 xy. Okay, so here it goes. 1/2 x, and in place of y, I'll put x cubed. And then I've got dx. And then I add that to the 1/4 x squared. And in place of dy, I'll put 3x squared dx. Okay, so let's see what we've got now. We've got the integral from 0 to 1, and we've got 1/2 x to the 4th plus 1/4, times 3, that's 3/4. 3/4 x to the 4th dx. Now let's see what we've got here. We've got the integral from 0 to 1, and I've got 1/2 plus 3/4, so that's going to be 5/4 x to the 4th dx. And we know that's going to be 1/4 because we already evaluated such an integral up here. Okay, so here's the thing we want to take note of. In all 3 of these paths, we got the integral 1/4, 1/4, 1/4, 1/4. And you might ask, well, is there anything special about this particular line integral? Well, what the special part lies in this vector field. This vector field is a special kind of vector field. And we've talked about this before. It's a conservative vector field. Now, let's go back up here and just test it to see if it is conservative. Remember what I'm going to do. I'm going to take the derivative with respect to x of this component, and that's just going to be 1/2 x. Okay, so I take the derivative with respect to x of that, and then I take the derivative with respect to y of this one, and that's going to be 1/2 x as well. So notice both of those are equal. The derivative of, so remember how it goes. The derivative of n with respect to x equal to the derivative of m with respect to y. When that happens, you have yourself a conservative vector field. Now what does that mean? Well, then that means that there is a potential function. And when we take the gradient of that function, we get the function, the vector field that we were looking at. In other words, there is some potential function, f, that when we take the gradient of it, we get this thing. We get 1/2 xy, and then 1/4 x squared. And we say, okay, that's a gradient field, and that makes that gradient field conservative. Now, I want to find that potential function. And, of course, we've learned how to do that in the past, but in this one, I can kind of eyeball it and say, I bet that potential function is maybe, well, let's try this. Let's do 1/4 x squared y squared. Something like that. Or x squared y. X squared y. X squared y. Whoops. X squared y. Yeah. So let me test that out. If I take the partial with respect to x, let's see what I get. I get 1/2 xy. Yes, that's the first part. And then if I take the partial with respect to y, I get 1/4 x squared. Yeah, so that is the potential function. Now, I want to show you something. In other words, it's kind of like the antiderivative of our vector field. Now, I want to show you something. If I take this antiderivative and evaluate it from the point 0, 0 to 1, 1, let's see what I get. I plug in the 1, 1. I get 1/4 1 squared times 1 minus 1/4, 0 squared times 0. Notice what I get. I get 1/4. In other words, it looks like I get the same thing that I get when I integrate along these three paths. I had 1/4, I had 1/4, and I had 1/4 on different paths. The straight line, the curves. I got the same integral. The integral came out to be 1/4. And here's the deal. When you have these conservative vector fields, it does not matter what path you take. So we had this point 0, 0 and 1, 1 right here. There's all kinds of paths we could have taken. Okay, just all kinds of paths. And if you have a conservative vector field, it's always going to give you the same result. So you might as well choose the simpler path. We had a real simple path up here, y equals x. And that gave us the same result as all those other two paths. So that's what happens when you have a conservative vector field. So when you're evaluating a line integral, you might want to check to see if it's conservative first. And if it is, you can just find the potential function and evaluate it. It's like a more general fundamental theorem of calculus. You get the antiderivative, the potential function. Plug in the destination point minus the initial point. Now, one more thing I want to say about this. If you end up back where you started, in other words, let's look at this situation. Let's suppose that you start here, you go to here, and then you go back. In other words, you have this closed thing. Well, then that integral, if it's a conservative vector field, that's going to be 0 if it's closed. Okay? Because you can imagine you're putting in the starting point, and then you're subtracting it off again. You're putting in your destination point. Your destination point is the same as your starting point. You can think of it that way. So when you see a closed interval like that, a closed region, and it's a conservative vector field, you know that integral is going to be 0.